The last lecture today. So final set of announcements for the semester. It's been a standard ritual from the beginning. Um, Nothing new. So you have your homework. No, not 6. Homework 5. I don't know why I make this mistake. Homework 5. Don't get concerned. I'm not going to release a new homework today. Um, Homework 5 is due today, and I know that most of you have already started. I hope. Um, it involves implementing SPM, logistic regression, and the good news is that parts of it can also be directly used for your project. And there's also an optional neural network question that you can work on if you're interested. There's a final project that's due today. And I hope you saw the announcement on Canvas. We've increased the number of submissions per day to 6. I say per day for today because the submission window closes today. But on popular request, I have decided to waive the late penalty for the report. So you basically get an extra day. I can't extend it beyond that because technically speaking, I believe I'm supposed to have all your submissions and all those things due before the exams start. There's some sort of a rule or something that I don't really understand that requires something, and I'm really not very keen on fighting that battle. But then what I can do is I can remove the late penalty. So I've decided to do that. So um, officially the deadline is still today. Let's make it clear. The deadline is today, but if you submit tomorrow, I will not complain. So you are allowed to submit till tomorrow. And the exam period starts right after that. And for better or worse, we've been assigned an exam time that's this week also. The exam is on Friday, April 25th at 10:30 a.m. in this room. Don't come here on Thursday for the exam because I won't be here. Any questions? Questions about the homework, the project, the final? Yes.
I guess will format and the final be pretty similar to the midterm?
Ballpark. I was telling someone I haven't yet finalized the final yet, so I'm considering it to be in the same style.
Like similar to what you said.
Maybe. You have 2 hours, so it might seem shorter, or maybe because you have 2 hours, I might decide to make it longer. You have 2 hours. It'll be doable in that. Other questions? If there are no questions, we're going to get into the actual content of the last lecture. What I like to do at the very end of the semester is after you've seen all these technical concepts involving machine learning, I like to take stock at what we've seen so far, but also connect it to more practical advice about building machine learning applications, deploying machine learning, and the kinds of things that you need to have in mind when you are actually using machine learning. We've seen a lot of technical content. Today's lecture is a little less technical, but I would argue maybe as important as anything technical that we've seen, because this is where the rubber meets the road. This lecture is about making machine learning work in real-world applications. And a lot of the content of this lecture is based on, let's say, mistakes that I've made, and also based on advice from a lot of people. There are some readings on the class website also. We'll be talking about a few different themes here. The first one is debugging. A lot of you have already kind of faced that problem. How do you know that your implementation is correct? How do you know that? How do you debug machine learning? Debugging standard code is in some sense a little bit easier because there's no random number generator inside. When you debug machine learning code, things get a little bit messy and it takes a lot more time to run, and you get feedback after everything finishes. So how do you conduct diagnostics of your machine learning code? Then I'll talk a little bit about this idea of error analysis. One of the most important things that you should be doing when you're applying machine learning out in the world, something that occasionally ends up being an afterthought, and it should not be that way. And I'll talk a little bit about that. Then I'll get into advice mode, talking about just things to keep in mind when you're introducing machine learning into something else that, something that matters to you. And speaking of machine learning or something that matters to you, I'll broaden the theme into making, how do you use the tools that you learned in this class to actually do something that's consequential out in the world? Because as you may be aware, AI is actually making an impact in the world, and you're going to be part of that. So, well, you are, of course, part of the world. So how do you use your power for good? So let's talk about all of these things. Starting off with diagnostics. Let's say you train, you build a spam detector. Let's say you train an SVM or a logistic regression, or maybe some sort of a neural network or something for your spam detector. Obviously, you do all the right things. You use the right strategies for choosing the hyperparameters. You don't just pick a random number for the hyperparameter and say, this is it. You do something like cross-validation, or maybe you use a validation set or something like that. And yet you find that your accuracy is only 75%. Maybe a good sort of a case study could be your project. You do all the right things and your F1 score is 60% or whatever it might be. What can you do to improve this? One obvious answer, one obvious place to look for is bugs in your code. But let's assume for today that you're perfect programmers. We don't make bugs. Let's say there are no bugs in your code. So then the problem is in how your code interacts with data, and maybe there's something going on there. So what can you do to improve it? Any ideas? Yes. Feature transformations, or more generally, changing the features, changing the representations. Yes, that's one idea. Yes.
Get more data.
Get more data. In fact, that's perhaps the most successful strategy that has been out there. When all else fails, get more data. Doesn't always work, because I was in a meeting yesterday where they were talking about getting more data, but when I asked that question, can you get more data? And the answer I got was every single data point takes about 14 days to acquire and costs $8,000. One data point, one example. So get more data is a valid answer until it's not. But it's something that you should always have in mind. Other ideas? Well, I tried to enumerate a few things. The first thought should be get more training data. When all else fails, look for more data. You could also play with the features. You could use more features. You could use less features. You could use different features. You could transform your features. You could do all sorts of things to your features. You could also change the way training works. You could train for more iterations. Maybe you use a different algorithm or a different model. Maybe you play with the way in which overfitting is controlled by playing with regularization or changing how dropout works, for example. The most important point here is there are many, many things you can do, and how do you know which of these you should do? So this process is not just tedious, but also every step along the way might introduce new errors that you may have to then go back and fix. And maybe there are dependencies across. Maybe you change the features and then you get data that's different from getting more data and then changing the features. So how do you make this more methodical? What I have here is like a list of suggestions for changes, but the question really is which of these things should be prioritized? And more importantly, when should you apply these kinds of ideas? So the first step should be diagnostics. It's easy to fix a problem when you know where the problem is. So let's consider some possible ways in which things can fail. Maybe you have a problem of overfitting, which sometimes is called high variance. Maybe you have a problem of underfitting, which sometimes is called high bias. Maybe your learner has not yet converged, or maybe, and this happens, number 4 happens so often that it should really be number 1. Maybe you're not measuring the right thing for your task. Maybe there is an improvement and you're not actually able to see it because you're measuring something incorrect. Your understanding of the problem could itself be the problem. Let's go through this one at a time. How do you detect overfitting or underfitting? Overfitting is where your data, your training data, is explained by the model far better than the model's ability to generalize to new examples. In other words, your model, your learner, has essentially produced a model that memorizes the training data really well. I may have mentioned a bad classifier sometime earlier in the semester. The bad classifier is something that I'll call the table classifier, where you take your training data, the learning algorithm is the following. You load your training data and put it in a table. Done. At prediction time, a new example comes in. You check if that example is in the table. If it's in the table, then you return the true label. If it's not in the table, you toss a coin. What would the training error for that particular classifier be? 0. Every single training example will get a perfect label. What would the generalization error be? As good as the right coin, whatever the coin's error is. So it is easy to create programs that memorize the training data. Another word that occasionally gets tossed around in this context is variance. Variance is the idea that your best classifier depends a little too well on the choice of your training data. So when you change the training data, the classifier's performance changes a lot. So if you just end up being very lucky and you get a good data set, then you get a good classifier. If you get a bad data set, you get a bad classifier. That means there's a high variance in the performance depending on the choice of the data. That's a bad thing because you don't get to control what data you get for the most part. The opposite problem is something called underfitting. It's not necessarily always an opposite problem, but I'll frame it that way. Where not only is the training error bad, the generalization error is also bad. Actually, the other way around. Not only is the generalization error bad, even the training error is bad. In other words, the model does not even have the capacity to represent the concept. So it doesn't matter whether it finds the true concept, it can't even represent the true concept. A classic example is maybe you're trying to learn an XOR type function, a parity type function using a linear classifier. Linear classifiers cannot represent parity, so you will have underfitting. Another situation could be your classifier, your model belongs to a certain family of functions, but the true concept is outside that family of functions, and there is not even a close approximation to that. That happens, that could happen. So this is sometimes called, this situation is described as the learner has a high bias, where even the best classifier has an unacceptably high training error. If the training error is really bad, then there's no hope that the true error will be good. So even your best classifier has an unacceptably high generalization error. So underfitting is said to happen when the bias is high. Yes.
Does underfitting is it universally means that we might not be able to reach the actual concept?
Yes. Yeah.
So
Why? What's the real question?
Because I've heard underfitting used as if safety data is linearly separable, but you don't run perceptual.
Yeah, actually that's another case where you have underfitting. I'm glad you brought that up. It's entirely possible that your learner has underfit because it has not yet converged. And we can say that also, but I'm using a slightly stricter definition here because even the best predictor is not good enough. That assumes that you've actually taken it to convergence. It's possible that your learner has not yet converged, and so that's why there the definition is slightly more constrained. It's the best predictor given the amount of time that you have. Is not good enough, then you are underfitting, not because your hypothesis space is bad, but because your learner is not given enough time. I've seen both definitions. Yeah. Yes.
So learning that is overfitting is better than underfitting.
Not necessarily. Both of them are going to have poor generalization error. Heavy overfitting. Take that table classifier that I mentioned. It's overfitting the training data, and it has if generalization error is as good as chance. Maybe there's an underfitting classifier that's slightly better than chance. We never know. So both of these can be bad. Both of these can be arbitrarily bad. I'll give you an example of a very, very bad case of underfitting. This is as extreme as that table classifier. My classifier, the model family, is a linear classifier in 0 dimensions. Meaning, you give me a data set with 100 features. I ignore all 100 features because, I want to have an efficient classifier. So what I do is I only have the bias term. And then I check when a new example comes in, I will check whether the bias term is greater than 0, and then I say true. Otherwise, I say false. And I don't need to check that for every new example because the bias term never changes. So before any data comes in, I decide I'm always going to predict true or false. That's as good as random guessing. That's, in fact, one of your dummy submissions for your project. That was an aggressive case of underfitting. That's also going to be as good as chance. That's the same as the majority baseline, or if you pick the label that has the majority label. So that can be as bad as overfitting also. So both these situations in the extreme can be really bad. I didn't need to tell you at that time, but when you submitted your dummy classifier, I was actually asking you to submit a heavy underfitting, a model, the prediction of a model that was heavily underfitting because it was just picking the majority label. And in some sense, you want your model to do at least as good as that. Any classifier that you train to do at least as good as that. There's a lot of literature on this trade-off between bias and variance. Did I miss a question? No. There's a lot of literature on this trade-off between bias and variance. And this is especially well developed in the context of regression, where you can formally say that the error of a regressor can be decomposed as some part of the error is because of bias, some part of it is because of variance, and then some part of the error is because you're just unlucky. Random noise, because of noise in the data or noise in the label or noise in your test set. High bias is where both training and test errors are unacceptably high, and your classifier cannot actually represent the data. High variance is when the training error is low, but the test error is unacceptably high. Your classifier, your model, your best model, represents the training data a little too well. Like I said, bias variance, there's sometimes it's positioned as a trade-off. You give up bias to increase, you try to control for variance, and sometimes the bias might increase. Some strategies that control for bias can lead to increase in variance and so on. This is especially studied in the context of regression, but there's been some work also for studying this trade-off in the context of classification. Sometimes you might see people talk about machine learning models and their bias and variance. Essentially, they're talking about overfitting and underfitting. It's important to be able to control for this. And different strategies, different learning algorithms that we encountered have different ways for trading off or managing bias and variance. So in general, ensembling reduces variance. Yes.
So when we're saying bias and variance, we're talking about basically test error versus train error, like how much are we biasing towards the.
No, when I say bias and variance, these are technical terms. Bias means your learner is exploring a hypothesis space that is not expressive enough. which means a way to diagnose that is that your training error is bad. Because even your training data cannot be explained by the model. So your hypothesis space must be small. It's not necessarily small, it's impoverished. High variance means your learner is exploring a hypothesis space that is so rich that it can end up explaining the data a little too well. So it has some connections to the size of the complexity of the function that you explore. Yes.
So I guess we find the variants like one of them in practice, what we did with SVM, where like you had to choose whether to.
Yes. And there's a sweet spot. You try to find the sweet spots. That's really how we manage bias and variance. So every learning strategy has different techniques for managing bias and variance. Often ensembling ends up reducing variance. When you combine multiple classifiers that are maybe trained on different subsets of data, each of them might end up explaining that particular subset really well, but the process of aggregating these ends up averaging out the variance, and that way you end up reducing the variance. Ensembling tends to reduce variance. It's a useful strategy, and there's a family of explanations for why ensembling works that focuses on this. That says ensembling works because it ends up reducing the variance, and that's because the error is a combination of bias and variance. By controlling the variance, you improve the error. When you have decision trees, and when you limit the depth, you are essentially increasing the bias. By limiting the depth of the decision tree, what you're saying is you're making the class of the trees less expressive. And if you're too aggressive about that, you might make it so unexpressive that it does not explain the training, it does not contain the true concept. So reducing the depth of the tree reduces the bias, increasing the depth of the tree reduces the variance. Sorry, I think I said it the other way around. Reducing the depth of the tree increases the bias, making the tree smaller increases the bias, making the trees larger increases the variance. Why does it increase the variance? Because if you allow the tree to get arbitrarily big, then it can fit whatever data really well. That means depending on the choice of your data, you might get a very good model or a very bad model, or the variation could be extremely high. For support vector machines, as you said, stronger regularization increases the bias, and stronger regularization means that your model can end up underfitting. Increasing the value of C in the way we formalize SVM can actually reduce the bias but increase the variance, because increasing the value of C puts a higher price for puts a higher emphasis on the loss. And the loss is essentially asking how bad is the model on the training data. Increasing C means the model has to be really good on the training data. Really good on the training data does not guarantee, but might end up increasing the variance. We did not talk about kernels at all this semester, and increasingly the broader machine learning community also does not talk about it, but there's this idea of kernels, and it's very intimately connected to the notion of feature transformations. So I'll explain that point in terms of feature transformations. Imagine that you have a feature transformation that consists of all degree 2 polynomials of your features. So if you have a feature x1 and x2, then you add x1 square, x1, x2, and x2 square also to your feature set. That's one feature transformation. Alternatively, let's consider degree 17 polynomials. All possible 17 monomials are in your features. 17, 6, not just 17, let's say up to 17, 17, 16, and so on. Increasing the degree of the polynomial in your feature transformation means you can draw complicated curves through the instance space, because increasing the degree of the polynomial allows you to draw more complicated curves. That means you might be able to come up with decision boundaries that might end up explaining the noise in the data. So increasing the degree of your feature transformation can increase the variance. linear classifiers are the lowest degree. They may have higher bias than a degree 2 polynomial, which has higher variance than the degree 1 polynomial. For neural networks, there's no such degrees of polynomials and so on. Often, increasing the depth tends to increase the variance but reduce the bias. Increasing the depth tends to make the model, or the width tends to make the model more expressive. So higher variance, lower bias. Notice that there are different techniques for each of these families of models, but the general impact is similar. More complex functions has higher variance, averaging has lower variance, less complex functions has higher bias. How do you detect? Yes.
There are cases where they're both high and they're both low, and how do you know which case?
We'll talk about diagnosis right now. So how do you detect high variance? So what you do is you plot these things called learning curves. There are a few different types of learning curves, and I'm talking about a specific kind here, where on the horizontal axis, you have the size of the training data. So you train many models on different amounts of training data. And on the vertical axis, you have the error. And when you have very little training data, it's so little that maybe your model can actually just remember the entire data. So the error is low, and eventually it will converge to something bigger. But let's say at each point, let's say you also measure error on data that the model never got to see. So it could be the held out data, test data, validation data, and I just call it generalization error here. And at the very beginning, on this very small amount of data, the generalization error might be very large, but maybe it goes down because as you see more data, the model gets better and better. So, but there's always going to be this gap here, right? Imagine that this gap is unacceptably large, and you have to decide what acceptable is. If there's a large gap between the train and the test error, it often suggests that you are overfitting the training data. That suggests high variance. If you change the training data, you might end up, this curve might end up going down somewhere else. Well, you'll never go below, but might end up going somewhere else. So the choice of the training data, which you don't get to control, affects drastically the performance of the model. And there's always a big gap between these two things. And that suggests that there's high variance. This is a good diagnostic for high variance. The exact same type of a curve is also a good diagnostic for high bias. High bias means the model is lousy even at predicting the training data, which means even the training error is unacceptably high. Let's say that line is the threshold for acceptability. Even the training error is unacceptably high, in which case the model does not even contain a good function to explain the data that it has seen. Generalization error tends to be higher than the training error, so it tends to be a little more. Sometimes, and if you are extremely unlucky, you might end up with a generalization error that looks like this, where the training error is high and the generalization error is much, much worse. You have high bias and high variance. You're working with a bad set of hypotheses, and somehow it's even worse on generalization time. I have not seen that, but I'm willing to concede that that could happen. So let's go back to this laundry list of model improvements and think about how these ideas can apply here. Usually, using more features helps with underfitting. Using fewer features helps with overfitting. Essentially, removing some features reduces the capacity. So using fewer features can help with overfitting. Using other features is, depending on what you do, it could help with overfitting or underfitting. I'm not willing to, this is just a blanket statement there. Playing with regularization or playing with dropout could help with both overfitting and with underfitting. Aggressive regularization can lead to underfitting. Aggressive dropout can lead to underfitting. So finding that sweet spot is necessary. And that's where a large part of modern machine learning is a huge engineering exercise. So, we talk about ChatGPT as being such an amazing tool, right? When I first saw ChatGPT, the first thing that I thought of was, this is a marvel of engineering. Having a server that's running with a model that is so big, and it does not crash, and it scales up to 1 million users in a week, and actually making it work, is an incredible act of engineering. And training that model with all the hyperparameter tuning. Now you understand the complexity of hyperparameter tuning. ChatGPT was a model that had many layers, many different bells and whistles, all the learning hyperparameters and architecture hyperparameters. And you need to train that, and each training run can cost $1 million. Isn't that amazing that it actually works? And then they keep releasing a new model every month. Okay, anyone who tells me that there's no room for programming anymore, I tell them to build ChatGPT, because if programming is a solved problem, then you must be able to build ChatGPT and keep it as stable. I'll help you out with all the modeling and everything, but you do the engineering. It's an incredible feat of engineering. So all of these tools are necessary for kind of making sure that you don't brute force your way through this. So we talked about overfitting and underfitting. It's also possible that your learning has not converged. It's always important to keep track of a different kind of a learning curve, and you're already plotting those for your homework. Here, on the horizontal axis, you're plotting the number of iterations, and this could be number of epochs, or increasingly more recently, the number of times your model is updated. So number of mini batches. And on the vertical axis, you plot the objective that you're minimizing. If learning is framed as an optimization problem and you're trying to minimize a certain function, then as your minimizer keeps running, in other words, as the number of iterations increases, the function that you're minimizing should go down. The value of the function should go down. Seems like a reasonable thing to do. When you plot this kind of a curve, you might notice that maybe there is, if you stop your learning here, it feels like the model is not yet converged. But if you stop it somewhere here, it feels like this has plateaued enough that the incremental benefit of running another iteration is not worth it. This is a sweet spot. But this is not always easy to decide, because imagine that your curve was falling like this. We can tell that the learning is not converged here, but what about here? Maybe this is after maybe 2 million epochs. You've run out of time. Are you going to stop learning, or are you going to just deal with it as, this is good enough? And this is just the objective. There's also the actual metric you might measure, and maybe if you measure the error on the test data, it goes up like this. So in a perfect world, maybe it was good if you had stopped there, but you don't have access to the test data. So it's not always obvious when to stop training. So one important thing to do is not just plot the objective. You should always plot the objective, because that helps you diagnose bugs. You should also plot accuracy, error, whatever, some metric on held out data. And you stop training when that curve starts to go the wrong direction. Yes.
I was wondering, like, you're not supposed to train on the test data,
Yes.
but like, are you allowed to see once it starts training?
Nope. You're not allowed to. You're not allowed to. That's a good question. That's a very good question. So let me write down. Let's call this test error. In a perfect world, if you use the test error, then you are essentially overfitting on the test data, because you pick the classifier that does well on the test data, and then you claim that it does well. Yeah, big whoop. That's not a big deal. So how do you actually get an estimate of the test error when you're not allowed to look at the test data? Yes.
You use a validation data.
You use a validation data set. You get a data set for training. You get to do whatever you want with that training data. One of the first things that's usually done is a tiny slice of that data is randomly sampled and set aside, and it's called the validation set. That's the data set on which you are tracking progress. And the rest of the data is the training data. So that validation data is your surrogate for the test data. And then you train on the training data and you evaluate on the validation data. Well, how much of the data should get into the validation data? If, for example, your validation set is 80% of the data that you got, and you train on 20%, that seems like you're just setting yourself up for failure, because more data always helps. On the other hand, if your validation data is 99.9% of the training data and you use one example for validation, you're setting yourself up for failure because your validation data is no longer representative of future. How do you know what's a good fraction? I don't know, 10% or 20%. It depends on how much data you have and how realistic you want your validation metrics to reflect test performance. And this is where we start making all these sort of design choices. And importantly, every single time you make such a choice, it's important that you document it, because these choices might make or break the eventual performance of your machine learning system. Every single design choice and every single hyperparameter choice should be documented. This is one of the most important things that you can do, because if someone else is trying to replicate your results and they're trying to read your mind without any documentation, they will probably not be able to replicate your results. So a part of all of this is documentation. Just like we have for software, for code, it's important to write comments, and nobody bothers to write comments, and your code ends up being a tangled piece of mess. With machine learning, nobody bothers to document their decisions, and your machine learning systems end up being a tangled mess in addition to the tangled mess that's your software. I'll talk about this problem in a bit, in a bit more detail, because it's a huge issue. All these curves are going down while training. But imagine your loss goes up, your loss behaves like this. We are minimizing a function, and then you find that that function is actually going up. That seems like there's a bug. Maybe it seems too much variation here, but there's a caveat. If you're doing gradient descent, this is definitely a bug. If you're doing stochastic gradient descent, you might find that your objective tends to increase occasionally locally. But if you run it long enough, if you find that your objective is increasing, then what you should do is run your optimizer for a lot more iterations. It should eventually start decreasing. Stochastic gradient descent might have locally bad decisions in terms of the objective value, but in expectation, the objective should be decreasing. Always track your objective. So adding more data helps with overfitting. Yes, I think I forgot to mention that before. Tracking the objective could help you figure out that maybe you need a different optimizer. Maybe stochastic gradient descent is not, the vanilla stochastic gradient descent is not the best optimizer. Maybe you need to use Adam, because there's too much variation across these different mini batches, and you want some stability in your optimizer. Maybe you want to use Adam. Or maybe you want to use, if you remember from the last lecture, all these optimizers have their own hyperparameters. Like momentum has its own hyperparameter, and Adam has a whole bunch of them. Maybe you need to use a different set of hyperparameters because your training is a bit unstable. Changing the classifier could also help with better generalization performance. And there, this curve might end up helping you. Okay. The last thing I wanted to mention is we should always think about evaluation before we implement any machine learning systems. The metric of success should be very clear upfront. Otherwise, you're not actually building anything that matters. I'll give you one sort of a flavor of this and then talk about this a little bit more. That's not a good sign.
So.
Yeah. So for folks on this side, is that visible? You have it on your screen. What about the last two rows there? Okay, I have no idea what's going on with this screen. Oh, it says the system power is off. Oh. Okay. That's the thing. We talk about AI and machine learning and intelligence and such things, but things like network cables, printers, and projectors are a mystery. Anyway, so I'll give you a simple example and then talk about something else. Suppose you want to measure the quality of a classifier. One of the most common ways to measure that is to measure accuracy. The accuracy of a classifier is really the fraction of mistakes that you make, that your classifier makes. Another thing you could measure is mean square error. That's for regression. Importantly, you should not be measuring mean square error for classification or accuracy for regression because it's not even the right metric. But let's say we are working with classifiers, and let's say that your data set and more generally your problem is extremely skewed in terms of the labels. Let's say one label, let's say positive examples occur 1,000 times more frequently than negative examples. And suppose I have a classifier that gets 99.9% accuracy. Do I have a meaningful classifier? I want you to take a stand on this. Yes.
That's on the real distribution.
This is the real distribution.
Like,
Positive examples are 1,000 times more common than negative examples. I'll give you an example of a classifier that gets 99.9% accuracy. I will always predict positive. My classifier takes the training example, a test example, tosses it out, and predicts the label positive. So let's say the classifier always predicts positive. I have 1,000 correct predictions divided by 1,001 data points. This is 99%. All I have to do to get a classifier that looks fantastic in terms of accuracy is to ignore the data and just predict the label plus. So clearly, when your data is unbalanced in terms of the labels, accuracy is no longer a good enough metric. And that's the reason for your projects. For your project data, we use precision and recall and F-score. Precision is precision recall in particular are defined on a per label basis. For each label, you have a precision and recall. So for a certain label, among the examples where the model has predicted the label, how precise is it? How many times among the pluses that the model predicts is the correct answer plus? The fraction of pluses divided by the number of pluses predicted, or the number of correct pluses divided by the total number of pluses predicted is the precision of the label plus. I could also have a precision for the label minus. Recall is the fraction of the true positives or the true negatives that the model has discovered. It's the number of correct pluses, the recall of plus, is the number of correct pluses divided by the true positive number of positive examples that exist in the data. How many of the positives has the model been able to recollect? Similarly, you have a recall for negative. The F-score is simply the harmonic mean of precision and recall. In other words, F-score is a number that satisfies. And if you solve this out, it really becomes F is, oh, this is R. And why do we use an F-score? Why do we could have taken just the arithmetic mean and made life easy. A couple of years ago, I tried to chase this down. And my best answer is this was an arbitrary choice that was made by someone in the 1970s. And in classic style, they didn't document it very well or at all. So, but we're stuck with it. It's really a number that trades off. You can, if your precision is perfect and your recall is 0, then your F score is 0.5. It's this thing in between. No, actually, no. If your precision is perfect and your recall is 0, your F score is 0 because recall shows up here. And similarly, if your precision is 0, but the recall is perfect, then your F score is 0. Anyway, but this is just a few standard metrics. Maybe there are other auxiliary metrics that matter for your application, and I'll give you examples of that in a little bit. It's important to understand the nature of the problem and the place in which your model will be applied to actually think about how evaluation works. And for that, the only way to go about that is actually to start understanding the domain of your application, the domain of your problem, not just treat it as a data set. Because if you start thinking of machine learning as just, oh, somebody gives me a data set, I press a button, I get a model, I send it out, you start falling into these traps where you measure the wrong thing. And you might be thinking that you're making progress because you have a fantastic model like this thing here, when in fact, underneath the hood, the model is actually doing nothing useful. Speaking of diagnosis, let's talk a little bit about this idea of error analysis. And now we are kind of stepping away from the low-level details into a little bit more about the application itself. In this entire semester, you've been looking at machine learning as if it's the main thing in your, or at least in this class. Machine learning has been the main thing. It's this big blocks that we are trying to unravel. It turns out in most standard industrial applications of machine learning, there is a box of that kind, and it's an important box, but there are other boxes. This is the little machine learning box here. This is a picture from a 2015 paper from Google, where they tried to point out how important machine learning was in the context of all the other things that they had in the pipeline. You need to collect data. That's a huge component. You need to think about feature extraction and storage and such things. You need to think about verifying and validating your data. You need to think about how you're going to orchestrate the machines where your code is running, analysis of data, managing all these things, and then deploying and then serving the models to a user, and then monitoring whether these models crash and then reloading this. All of this, all these boxes outside, except for that little black box in the middle, these days people call it ML ops. And honestly, it's so much engineering. It's engineering, software engineering of the kind that you might learn in a software engineering class, except with this little box inside that throws out probabilities and makes mistakes stochastically, which keeps the engineers on their toes. The problem with this sort of systems is if you're not careful about the design and maintenance of these systems, you end up with trouble very soon. Again, from Google, there were a few papers that called machine learning the high-interest credit card, where you might think that you're winning right now, but later on down the line, the interest is going to hit you. It's technical debt in that if you do not document your code, if you do not document your design decisions, 6 months down the line, your future you will hate the current you. Because even you might not know why. Like, okay, I've actually personally faced this. I mean, like I have a certain design choice that I have no memory of making, but I'm stuck with it because we've made the choice, we've invested infrastructure into it, we can't go back in time and fix it, and I have no idea why that choice is there. So the lesson here is think of machine learning as a piece inside a larger context and document all your design decisions. But error analysis is still a part that I haven't talked about. Machine learning plays a small role, but an important role in a larger context. And there are a whole bunch of assumptions that are in place at every step along the way. If you're lucky, you get to be involved in the process that gathers data. If you're lucky, you get to be involved in the process that pre-processes the data from or does feature extraction or whatever. Or whatever transformations you might make. If you're lucky, you might be involved in the user interface that interacts with the people who use your systems. And the problem is that other than in these sort of toy contexts like we look at in the class, the users of your machine learning system are not going to be working with the classifiers to measure precision, recall, F1, accuracy, or whatever. They're going to be working with it through an interface. And they don't really care, for the most part. They don't care that you used a 2-layer perceptron or a 15-layer transformer network. They just want their thing done. So imagine that your system has errors. Your user is not happy. How do you know which component of all of these things led to the problem? Error analysis is the process of systematically uncovering what in this entire set of steps contributes to errors and how much. That allows you to actually fix errors that are not necessarily just machine learning related, but come in from the broader context. I'll give you an example here. In a text processing pipeline, that used to be the standard operating procedure until maybe 5 years ago. Now nobody does what I'm going to say, but since I made a slide, I'm going to keep it. Imagine that you have some text. And the standard pipeline here was to first convert the text into words. It's called tokenization. And then you have a classifier that predicts some parts of speech for the words. Then you have some other model that predicts parse trees. If you don't know what they mean, they're just a structural representation of the text. And then all of these things go into some ML-based application. Often the only thing that people cared about was this thing here. But maybe the error into that system was introduced at this point. How do you know that the error happened there? Each of these pieces could be deterministic, they could be heuristic, or they could be statistical. And so each of these things could contribute to different amounts of error. So how do you know how much error this is, how much do each of these pieces contribute to the error? One way of addressing that is for each pre-processing step, you take the painful effort of removing the heuristic or the error, heuristic process, and actually creating the ground truth. So we have an end-to-end system, let's say, that gets a 55% accuracy. And you need to know where the error is coming from. Maybe you replace this process of constructing words by manually tokenizing the sentence. Maybe there was a bug in your code, or maybe there's some choices in your tokenizer that are not sound, but it's been there because someone else wrote the code and you don't want to change it. So you replace the end-to-end prediction with ground truth tokenization, you get a 5% boost. Maybe you hire a linguist and you have them annotate parts of speech and parse trees. You find that with ground truth parse trees, you further get an improvement of 24%. Improving to better parse trees gives you a little bit more, and introducing the ground truth label get you 100%. That's a sanity check. A system that has the ground truth label should get nothing worse than 100% because it has the ground truth label. That's an error evaluation. If it does not, there's a bug in your evaluation code. In any case, this process might tell you that the most important thing to focus on is better parts of speech because this jump is the highest. That allows you to think about not the machine learning part, but the process, the pipeline that feeds data into the machine learning. Where does the error happen? So you're not thinking of machine learning as just a tiny bit, but a broader application. So the error in the parts of speech hurts most. So maybe you want to dedicate your resources to building a better part of speech tagger. This style of another sort of analysis tool is something called an ablation, where you have a strong model and a weaker model, and you're trying to explain the difference between these models. And one way of doing that is you start off with a strong model. You want to understand why the strong model works. You make it simpler and simpler by taking all of these design choices you have and considering a simpler alternative. And then you will understand which of these design choices contributes most to the performance. The key lesson here is it's not sufficient to have a classifier that works. It's important to understand why it works. Otherwise, you have a black box that you can't control. It helps you understanding why it works, allows you to extend it. It allows you to diagnose errors. And if necessary, it provides an audit trail so that if someone comes after you and says, your system denied my loan, you can actually tell them, oh yeah, it's because of these things. So it allows for an audit trail, so it helps you eventually. Machine learning systems tend to be used in broader context. So in that sense, I have this picture here of a machine learning protest that took place in CMU around 2009 or something, where they were talking about supporting vector machines and having Bayesians against discrimination. But really, the question I want to ask you here is how many people are in this picture? The contrast here is bad, but you can still kind of take a guess. So some people say 5. Imagine that you do this with a machine learning system. And you're going to do this, let's say that you're doing this in a somewhat convoluted way, where you have a leg classifier, a head classifier, and a hand classifier. So you have 3 heads, 3 hands, and 4 legs. You know, at best about 3 to 3.5 people. And yet, we seem to agree that there are 5 people here. There are 5 people because there's one, this is one person, this is one person here, this is one person, and this is one person here. Oh, I realize you can't see the contrast there. So 1, 2, 3, 4, and 5. There are 5 people here, but if you count the legs and heads, it doesn't work. The real point I'm trying to make here is learned systems are not used in isolation. They are used in combination with each other. The uncertainty of one system percolates into the uncertainty of the other. And all these uncertainties are going to kind of add up, and you need to operate. When you're building applications, you need to account for these kinds of interactions of learned systems with deterministic systems and making sure that they kind of work well in conjunction. Let's talk about how you might inject machine learning into your favorite task. When I was making this slide, of course, I did not know what your favorite task is. So I picked a task that's definitely not my favorite. Imagine that you have a system that for some reason you need to classify fish as salmon or tuna. And how do you go about this? How do you use machine learning to decide whether a fish is salmon or tuna? There are, at this point, there's like you need to collect data, you need to do all that stuff. But high level, there are 2 types of approaches. There are 2 approaches. One of them is what I'm calling the slow approach, where you carefully identify the right features, you get the best data, you build the software infrastructure. Maybe you even invent a new learning algorithm, and then you implement it and hope it works. The advantage of this is it can lead to better approaches. This is how science and research operates. There's also the hacker's approach. You first implement something, and then hope it works. It's not going to work because you just spent half an hour doing it. And then you use all these diagnostics to figure out what to focus on next and improve that part. And then you keep iterating. This allows you to have solutions that you can deploy, and this is often the way in which you make money. I'm not saying that there's no money in research. I'm also not saying that there is money in research. But I think some combination of both of these is important. Don't be careful of prematurely optimizing. Be careful of prematurely committing to design decisions and choices. That's often a problem with the slow approach. Be at the same time careful of this sort of a greedy algorithm where you implement something and that then you're committed to a certain path without thinking. Both of these are bad, and of course, this is a life lesson. Don't do either of these. Things to watch out for: random collection of text. Do you have the right evaluation metric? And does your loss actually reflect the thing you want to measure? One of the most important things that you need to be careful about, to the point where it should be second nature, is you should always be wary of data contamination. These days, I'm a lot less wary of it with my own work, but I know that there is data contamination in a lot of machine learning systems out there. The goal of learning is generalization. If you cannot generalize to new examples, you do not have a learning-based system, which means your classifier should not see the test set. Your learning algorithm should not see the test set. I would recommend you should not see the test set, because you might contaminate your learner through certain design choices that you inadvertently introduced because you looked at the test set and you saw that there's a certain example there and you want to get the label right on it. A common bug, not a common, there's a certain bug that you make that happens once in your life, and after that you'll always be wary, where you might get your data as a CSV file, as a table. One of the columns is the label. You create a feature for that column. One of your features is the label, and you get 100% classifier, 100% accurate, 100% F1, 100% everything, because all the classifier does is it copies the label over. I'm generally very, very suspicious of perfect classifiers. For anything but the most simplest of applications, perfect classifiers tend to be a sign that there might be a bug of this kind. Be aware of this trade-off between bias and variance, or of the trade-off between overfitting and underfitting, and you might have to take steps to counter for that. Something we did not really talk about this semester because we didn't have time to get into that, is something called the curse of dimensionality. And there are many different versions of that, and I have some slides on that in the chapter, in the lecture on nearest neighbors, if you're interested. But the general idea is that intuitions that work for 2 or 3 dimensions don't necessarily translate to high dimensions. Higher dimensions act weird. So always think of, anytime you see proof by pictures, you should be a little suspicious. Speaking of proofs, we spent some time talking about the theoretical part of machine learning. It's entirely possible that the theoretical guarantees are only theoretical and don't actually translate to anything in practice. Every single theorem that exists has the following shape. If a certain set of conditions hold, then some conclusion holds. Maybe those set of conditions never hold in real life. Who cares whether the conclusion holds? Maybe it doesn't really connect to anything you care about. Maybe it makes invalid assumptions. Maybe, like for example, we saw a theorem that made a wildly invalid assumption. The perceptron mistake bound theorem. If the data is linearly separable, the perceptron will find a separator. Good luck finding a data set that's linearly separable. Sometimes these guarantees might only be meaningful with infinite data. Stochastic gradient descent will find you the local optimum if you let it to run to infinity. In practice, so you always need to do empirical experiments. Experiments on data are as important as theory, and theory, I think, is also as important as experiments. I personally enjoy both of them. We keep hearing about how much data is important, but big data is not always the only answer. More data is almost always better. Cleaner data is even better. But remember, the most critical thing that we encountered multiple times this semester is learning without any assumption, any sort of bias that guides your learner is a futile effort. We looked at different kinds of these assumptions, where restricting the hypothesis space, for instance, or assuming that the data is linearly separable, assuming that a 2-layer network is good enough, knowing that we see these assumptions for other bigger applications. One example is that for image classification, for instance. For image classification, let's say I need to detect an object in an image. If I have an image and I just take the mirror image of that image, the object doesn't change. So image classification has this property called these sorts of invariances. So your model should, the model family or your loss function or your learning algorithm, something should capture that invariance. Learning almost always requires knowledge to guide the learner, to guide the choice of the classifier, to guide the choice of the hypothesis space, your learner, your design, all the design choices. Machine learning is clearly not a magic wand. It's not gonna, you can't just sprinkle fairy dust on your problem and hope that it works, because there are all these empirical engineering decisions that need to be made. Otherwise, things will definitely not work. Or maybe even worse, objectively worse, it might trick you into thinking that it's working today, and when it really matters, it fails. What knowledge? One kind of knowledge is what family of models is necessary for the problem. What learning algorithm is needed. Learning algorithms all come with assumptions, and maybe this choice matters. Feature engineering is an important design choice. If you get the right features, machine learning is easy. If you get the wrong features, machine learning is impossible. And implicitly, all these choices are assumptions that you're making about the nature of the problem, which means it's important that you understand the nature of the problem. Other advice that I couldn't put a title on. I personally like trying out simpler models first. It's just a personal choice, because if simpler things work, then I don't want to try the complex things. And if they don't work, at least they form a baseline that then you can compare your next thing against. Ensembles tend to work better, so just keep that in mind. And it's an important thing to know whether your problem is actually learnable at all. Learnability is the same as being able to generalize. And certain problems are not learnable. A random number generator cannot be learned because it's the opposite of learnable. There is no generalization. So it's important to know how much learning can help. In the last maybe 10 minutes or so, I want to talk about how machine learning can matter in the broader world. In 2012, there was every year we have this conference called the International Conference of Machine Learning, ICML. At the start of the semester, I showed you an example from ICML 1994 with the badges game. Here I'm showing you something from ICML 2012, where there was a keynote lecture by Kiri Wagstaff. Kiri was actually, she did her undergrad here, right here at Utah, and then went on to do a PhD at Cornell, I think Cornell, and then worked for NASA on some Mars mission stuff, and he was using machine learning in that context. And she, 2012, this is more than a decade ago now, she asked the broader machine learning community to take on more challenging questions. So can there be a law or a legal decision that relies on the output of a machine learning system? Has $100 million been, can we save $100 million somehow because of decisions provided by an ML system? Can we avoid conflict between nations because of translation provided by an ML system? I don't know about avoiding conflict between nations, but translation today is very, very robust. Can we improve cybersecurity and reduce break-ins by 50%? One person's life has been saved because of a machine learning-based intervention. I love that point is as important as $100 million and as important as conflict between nations. I don't know why. I find that very oddly satisfying. Maybe there's a 10% improvement in a country's human development index because of an ML system. Some of these things are grand challenges. Some of these things, small versions of those seem like they are doable today. But I think the broader question still remains. As people who are learning the technological tools, namely you, I think it's important to also keep the broader context of where these tools are getting deployed. Data-driven decision-making, often powered by machine learning, is incredibly widely prevalent today. And when the field of machine learning was in its infancy, these ideas were just proof of concept. I have a toy data set on which I can get 90% accuracy. It doesn't affect anybody. Today, because they actually affect people, broader concerns about algorithmic decision making starts to become important. Maybe these classifiers exhibit certain types of undesirable biases. Maybe the data sets exhibit undesirable biases. How do we know that the systems that we are building are transparent? And for the next few minutes, everything I'm going to talk about is going to be in the form of a question, because honestly, I have no answers. These are things that we should all work together on. When can we believe your model? Should you actually leave decision making entirely to the model? Can you do that? And how do you know that it's working? What if these models are used in ways that are not particularly savory? These are, we talked about accuracy, F1, and such things. These are all auxiliary criteria that are not part of any loss function. It's not even clear how to convert this into loss function. How do we even optimize for these things? And it's not necessarily purely a technical challenge. Classifiers can be biased. And what if this classifier decides that, let's say you apply for a loan, and instead of actually a human looking at your application, it's fed into a statistical system, it reads your application and decides that you should not be given the loan. Why? Because layer number 15 of the transformer neural network had certain weights. That seems like an unsatisfactory answer. Or maybe someone is denied bail, or maybe someone is fired from their job because of a machine learning decision. I say maybe, but there are actually real life examples where these things have happened. Yes.
But I guess the example of that is I know in the writing department, they're implementing AI to read people's papers if they want to take classes. Like, instead of like having to take writing like 1040 or something, they can skip the 240.
I will reserve my comments because this is recorded. The thing is, how do you ensure that your models are not used in morally dubious ways? And this is a broad question of fairness of machine learning systems. Another way of thinking about it is how do we ensure that the tools that we build don't do any harm? I think it's the responsibility of the tool builders as well as the tool users to ensure that. This is something that percolates the entire pipeline from the process from which the data is collected to the place where it's deployed, to every design decision along the way. You might need to think about it. Let's say the classifier decides to fire you. If it's not a classifier, if it's a real person who's firing you, you're well within your rights to ask why. Can you ask the same question to a classifier? Isn't that an amazing sort of a technical question? Can we develop methods that not only make predictions, so explain their predictions in a way that a human can understand? This idea of interpretable machine learning is a very, very important topic of both research and practical use. How do we develop algorithms that explain their decisions? We don't have all the answers here. And this is an open question, because when we talk about explanation, we need to talk about explaining to whom. Imagine that you have a classifier that is making some decision about your grandma. And the explanation is that feature number 18 has a weight 41. And that's why the decision was made. I don't know about your grandma, but my grandma would be very confused. Explanation is an act of communication. How do we build models that can actually do that in a way that aligns with the underlying decision-making process? Because these systems are starting to get more and more impactful in real life, there's a broader question of whether our legal systems are even capable of handling these sorts of things. I was talking to someone in the legislature about this, and the question of what if evidence gets faked by an AI system? How do we know? How can we trust any information that we encounter? What if an automatic, self-driving car drives into someone? Who is to blame? Is it the owner of the car? Is it the organization that made the car? Is it the person who wrote the algorithm? Is it the training data that was collected? The blame is rather diffuse, and our legal systems are not entirely equipped today to handle that. And there are other sort of complicated issues that we have to deal with the legal system. All of these ideas are often in the last few years, these have coalesced into these questions of fairness, accountability, and transparency of decision-making systems. We want to ensure that our algorithms are fair. We want to ensure that our algorithms can be held accountable and that they are transparent. But the problem is, these are all such vague ideas. It's easy to say that the loss function is max of 0,1 minus YW transpose X. It's very hard to say this is a mathematical definition of accountability. These ideas are all part of an annual conference, discussed in an annual conference called FACT conference. If you're interested, you should check it out. In the 2 minutes that are left, I want to just look back at the semester that we had. The very first lecture, I had this picture that tried to define machine learning somewhat formally. And after that, through the semester, we saw different kinds of models. These are functions that your learning algorithm learns: linear classifiers, decision trees, neural networks, ensembles, and such things. We saw only one learning protocol throughout the semester: supervised learning. But there are others. There's unsupervised learning, there's reinforcement learning, there's semi-supervised learning. We saw different kinds of learning algorithms. One of them was online, which was Perceptron, where the learner accesses one labeled example at a time, makes an update, and it lives on forever. Batch algorithms where the learner has the whole data set, and most of the algorithms that we saw this semester were batch algorithms. We talked a lot about the importance of representing data. Feature representations are important. Maybe you want to learn those features, and neural networks do that. The whole semester was kind of held together by this question of what does it mean to learn? We saw 3 different ways of defining learning: online learning, pack learning, and Bayesian. And each way to answer this question opened up the door to a collection of ways of thinking and a collection of algorithms. Pedro Domingos put together a collection of many different ideas that show up in machine learning. This was in 2012. This box has become much, much bigger now. But the most important point here is, despite this diversity of ideas, machine learning is remarkably easy. You might disagree with me because there's an exam this week. But in practice, many of these approaches work just as well. You can use an SVM or a logistic regression, and a well-tuned one will work just as well as the other. What we did not see is probably much bigger than what we did see. It's a vast area, it's large, it's growing, and there are many, many topics that we did not cover. But really, my hope this semester has been to kind of instill in you this sort of way of thinking about machine learning, the foundational ideas of how to think about machine learning, hopefully with the goal that when you encounter these other things, you'll be able to pick up those things because you have a conceptual framework. There are many different classes that you could follow this up with. Every semester this changes, but these tend to get offered in the School of Computing. They're like AI classes, data mining, theory classes, visualization. There are various specializations and so on, and various applications as well. In this class, the focus was to kind of build this foundational understanding of the underlying concepts and the ideas that drive them. And it's not about any one tool, even though along the way you saw some tools. What we saw was this theoretical understanding and a practical understanding of what machine learning is. You gained the ability through your homeworks and project, the ability to implement essentially an entire new machine learning library. And hopefully through your projects and such things, you got to identify where machine learning might work and how to make it work. Thank you so much for the semester. I really enjoyed teaching this class. I've taught this class for 10 years, and every single semester I've taught it, I learned something new about machine learning, and this one has not been different in that sense. So I thank you so much.